Hey guys, hope everybody's doing okay. What we're going to do today is take a look at something called the Châtelier's principle. This is a really neat lesson that ties together a lot of what we've been talking about with equilibrium. And it's really interesting because it gives us an opportunity to see how we can manipulate an equilibrium system to basically do what we want it to do. So if we want to create more reactant or more product, we can figure out how to do that. So there are some practical real-life applications to this. We'll get to that at the very end of the lesson, and a couple interspersed throughout it. And it also leads us into a really neat LeChatelier's principle lab that we're going to do, where we'll get to look at a bunch of equilibrium systems, and we'll change something about them. We might change a concentration or a pressure or a temperature of one of the systems, and we'll see how the reaction will shift to counteract that and to see how that all works. So let's get right into it and start with the formal definition of LeChatelier's principle. Formal definition says if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration, the system will shift its equilibrium so as to counteract the effect of the disturbance. So what this means is, in simple terms, is if you change something about your equilibrium system, temperature, pressure, or concentration, the equilibrium system will find a way to undo that stress or undo that change you placed on the system. All right? So it's really interesting how that all happens. So if you increase the temperature of your system, equilibrium will shift in a direction as to counteract that and to decrease the temperature. If you were to decrease the pressure somehow, equilibrium would shift in order to increase it again. So it's really neat how this stuff works, and the lab is really cool because we can see how equilibrium moves to counteract the stress that you place on it. So as LeChatelier famously said, weevils wobble but they don't fall down. That's the image here in the bottom right hand corner. I showed you that as we introduced this unit, and we took a look at I think the first lesson when I taught equilibrium constants. So equilibrium finds a way, right? So what we talked about throughout the unit so far, and it's no different here. It finds a way to counteract the stress you place on the system. It finds a way to keep that KEQ or KC or KP value the same. All right. The only time that is not going to be the case is in the case of temperature. All right. So temperature is going to always change our KEQ or KC value, but change in pressure, change in concentration, that is not going to change our KC or KEQ value, and we've talked about that before. So temperature is the only thing here that's going to change that KEQ or KC, KP value, whatever it is. So we'll take a look at concentration first, and when we change concentration, what does that do to our equilibrium system? So simple equilibrium system here, I have A plus B yields AB. So the red is your A, the blue is your B, and here's our compound AB over here. Right now it's at equilibrium because Q is equal to K, but let's change something about it and see what happens. First thing you should do in your notes is calculate the KEQ value. So let's knock that out real quick. So KEQ is your products, which is your AB, over your reactants, which is A times B. All the coefficients are 1, so everything is raised to the first power here. So the KEQ value is going to be how many products you have, which if you count them up, there's 22 of them. I'm not going to put the brackets here to save some time and make it less sloppy, over your reactants. So A, if you count them up, you have 11 of them. And for B, you have 14 blues. Okay, so 11 A's, 14 B's, 14 blues. Figure it out, you get a KC value of 0.14. All right, so that's important. That's our equilibrium constant for this reaction. So let's go here and let's add more A to this reaction. So A is the red. Okay, so I added more A to this reaction. What did that do? So we want to think of this as increasing the concentration of A, whatever substance A is. So when I increase the concentration, this is my snapshot in time for this reaction here. I need to figure out what did I do to equilibrium here. Well, I messed it up, obviously. How did I mess it up? Let's figure that out. We want to find out what our Q value is. Okay, so that was a previous lesson. So Q is the same formula, right? Q equals AB over A times B. But this is our snapshot in time, right? Because we just added the stress to the reaction. we need to see how is the reaction going to move to undo that stress. So if we count everything up again, Q is equal to 22 over, now I added some A, I now have 16 of those. And B didn't change, I have 14 of those. So it has you calculate this in your notes. Our Q value comes out to be 0.098. Okay, so you ask yourself, what does that mean? Well, right here kind of gives it away. Q is less than K, right? Our Q value is 0.098, K is 0.14. What does that mean if you go back to your reaction quotient and puzzle lesson? Well, if Q is less than K, we need to make this ratio bigger again. Okay, how do we make it bigger again? I have to increase my product and decrease my reactant. So equilibrium is going to have to shift to the right, okay, to undo that stress. So I added the stress to the reaction, which was adding more A. I need to undo that stress by shifting to the product side. That will make my Q value bigger again. So let's actually shift to the product side. I'll click that arrow. Okay, so we made some product. I could recalculate Q here. I'll do that real quick. So Q is now, when I move to the product side a little bit, Q is going to be equal to 23 over 15 times 13. And that's going to give you a Q value of 0.12. So you can see we're still less than what we're supposed to have. We need to get up to 0.14. You can see how shifting the reaction to the product side increased our Q value a little bit. Let's do it again. Okay, more went over. And now the simulation tells us that Q is equal to K, which apparently is good, which it is. So if I figure out my Q value again, okay, my final Q value here, Q is equal to 24 over 14 times 12. And that'll give you a Q value of 0.14, which is the same as your KEQ value. So as we shifted to the product side, equilibrium was reestablished. So Q is equal to KEQ. And you know that because your Q and KEQ values end up being the same again. Okay? So that's how we want to deal with stress on the reaction when you add a either increase or decrease the concentration of something, either a reactant or a product. How does Q change? Okay? And then how does the reaction proceed and shift to undo that change? So it really is a reaction quotient problem when we change concentration. All right? So what is the same here for this? The same ends up being your KEQ value, right? KEQ does not change here. We end up shifting so we get the same KEQ value. What's different though? What's different is the concentration of product and the concentration of reactant. But the ratio remains the same. Okay, the ratio is clearly 0.14 before and after. Before your shift and then of course after it. But the actual concentrations are different. We had initial concentrations of 22, 11, and 14, and then we added the stress, right? The reaction proceeded to undo that stress. We ended up with 24, 14, and 12 as our concentration. So they're different, but the ratio remains the same. So let's take a look at another example here. If I can get this to actually move ahead a slide. There we go. Okay, so which accurately reflects the changes in concentration that will occur if O2 is added to disturb the equilibrium in this system. All right, so we're adding some O2 to that system. We're increasing that. So automatically we know that this is the wrong answer and this is the wrong answer. Okay, so we increase the concentration of oxygen gas. Okay, so think about what happens here. We don't know any numbers, but we don't need to. So the question says, what happened to Q when oxygen was added? All right, so Q is equal to products over reactants. So we have NO2 squared over NO squared times O2. All right, if you increase the concentration of O2, you increased something in your denominator. So what happened to Q compared to KEQ? So when oxygen was added, Q ends up being less than KEQ. All All right, so we were at equilibrium at first. We added a stress to the system. We added a reactant. So you go to your Q expression. We increased our denominator, which makes this fraction smaller. So Q becomes less than KEQ. So you have to ask yourself, what direction does the reaction shift in? Well, if Q is less than KEQ, the reaction should proceed to the product side. So as that happens, we're going to go this way. Right, we're proceeding to the product side. Right? As you shift to the right, to the product side, we're going to increase our product concentration of NO2, and we're going to decrease our reactant concentration of NO. Right? So we're going to decrease NO. Looks like that'll work. We know we're increasing O2 because that was the stress I placed on the system, and I'm going to increase my product. So the correct answer is number 5. All right? The proper explanation is what you should write down on your note sheet. This is really, really important, so you can pause the video and jot it down. And when you look at this, it says when oxygen, a reactant, was added, the Q value decreased. The College Board is big on this, all right? So anytime you change a concentration, whether it's of a reactant or a product, you can't just say there's a stress on the system so it shifted in a particular direction. You have to mention Q, all right? So you have to mention Q when the concentration changes. So write that down, okay? And make sure you have this proper explanation here to tell me what Q does, then how does the reaction shift to counteract that change in Q. All right? And that basically takes care of concentration. The next one is a change in temperature. So I did this demo for you as we started the unit. Here's my cobalt ionic solution here. You can see my cobalt chloride type solution here, COCl4, is blue in hot water. Okay, so this is hot water over here. And in cold water, it is pink. So this is cold. Okay? So what we want to do is take a look at, is this reaction endo or exothermic? So you got to see where the heat variable is. Heat is on the reactant side. So if heat or energy is on the reactant side, what does that mean? Well, it means it's an endothermic reaction. Okay, so this is endothermic. So this is really neat because if you place your test tube, now the same thing is in both test tubes here, right? Just a before and after, a hot test tube and a cold one. If you place your test tube in a hot water bath, which is what we have here on the left, what's that mean? Well, you place the test tube in something that's hot, so what's it going to try to do? Equilibrium is going to try to find a way to move in a direction where you use up that extra energy from placing it in the hot water bath. All right? So you place it in the hot water bath, the reaction should try to use up that extra energy that was added from the hot water bath. So if the reaction were to progress to the right, okay, in the forward direction, that would make sense, right? Because if it's an endothermic reaction, as the reaction proceeds to the right, as it proceeds in the forward direction here, that energy is used up, right? That's what endothermic is. Energy is being put in, you're using it up. So the reaction is trying to cool itself down by using that energy from the hot water bath. Well, look what happens. As it proceeds to the right, you end up with COCl4, which is that blue color, okay? So if I clear this out real quick, if I place it in the cold water bath, what's that mean then? Well, if I place it in a cold water bath, equilibrium is going to say, hey, I need to heat this back up again, right? So it's going to try to go in a direction where energy is produced, right? And energy is given off in the form of heat, right? So we're trying to make that warmer again. So if it's an endothermic reaction, in the forward direction, then if the reaction were to proceed backwards, okay, in the reverse direction, then it's going to be the opposite, right? So the forward reaction is endothermic. The reverse reaction is exothermic. And heat will be produced, okay? So if you place this in a cold water bath, the temperature is going to try to go back up again. So heat's released and produced, right? So the reaction will proceed in the reverse direction. And look, the cobalt solution you have turns pink. So it's really, really neat how that happens. So you keep going back and forth like my flasks I had for the demo, and you can see how the color is going to change. So if you take a look at the examples on your note sheet, it says what's true about the KEQ value of the same reaction at different temperatures. The same reaction at different temperatures will have a different KEQ value. All right, so this is one here. It's a star. This is one here where the KEQ value does change when your stress changes the equilibrium system, right? It's the only time that happens. So if you take a look at the first example, H2 plus I2 yields 2HI plus energy. Energy is on the product side. This goes way back to some Chem 1 and some Unit 1 stuff, actually. This is an exothermic reaction. Okay? So if your reaction is exothermic, energy is on the product side. An increase in temperature, okay, an increase in temperature means your reaction then wants to try to decrease the temperature, okay? So the stress is increasing the temperature. The reaction will shift in a way as to use up that energy that was added from that increase in temperature. So in order to use up the energy, this reaction needs to proceed backwards, okay? If the reaction goes in the forward direction, you're producing energy. It's exothermic, right? That production of energy is going to increase the temperature even more, right? So we want to make sure our reaction goes to the left in this case, because as it goes to the left, energy is being used up here. That increased energy from the increased temperature is being used up, so we shift in the reverse direction. If you have a decrease in temperature, the reaction is going to want to try to increase that temperature again. So the energy variable should be a product if you're trying to increase the temperature again. Well, it already is, so the reaction will continue more so to the product side and to the right. Okay? Now look at the other one. It's an endothermic reaction because energy is on the reactant side. So this is similar to the example on the previous slide. So if you have an increase in temperature, which way do you think the reaction is going to shift? Well, the reaction is going to try to shift in a way to use up that extra energy from that increase in temperature. So this reaction is already using up energy. It's endothermic. So if the reaction goes more to the product side, it will use up more and more of that energy. So the reaction will shift to the right. Okay? Now, if I have a decrease in temperature, the reaction is going to try to increase it again. So I need energy as a product. Well, the way the reaction is written, energy is a reactant. If I reverse the reaction, energy now becomes a product, and I'm moving in that reverse direction. So equilibrium will shift to the left. Okay? Don't memorize any of this. Like, you'll get all confused, you'll make a million mistakes. What you need to do is just think a little bit and think, okay, if the reaction is increasing in temperature, okay, or decreasing in temperature, how do I undo that? So if it increases in temperature, you want to use it up. You want to use up energy. And if you're decreasing in temperature, you want to make sure you release energy and increase the energy again. So how does my reaction shift in order to either decrease the temperature if my stress was an increase, or how do I increase the temperature if my stress was a decrease in it? All right. It all depends on if you have an endo or exothermic process to start with, and then obviously just see how you want your reaction to proceed. This one, I would say, is the trickiest of the three, just because you have endo and exo reactions, and then you have an increase or a decrease in temperature. You got to think of what way your reaction is going to shift. Okay, so we'll do more practice in the lab and in class on that. A really good example of this is light-darkening glasses. So you have ever seen these? It's like if you're indoors, it looks like a regular pair of glasses, and then if you go outside where it's sunny, they automatically turn into sunglasses without you doing anything. All right, so it's pretty cool. The picture in the bottom left shows that. So you have your regular indoor glasses here, and then you go outside, they darken. So it's all about Châtelier's principle and why that works. It's really neat. So the glasses themselves are pretty complicated, but you have basically two components here. You have a silver chloride component that's clear, and a silver, like actual silver metal component that's dark. And energy is on the reactant side. So we have an endothermic process for this. So when you go outside, the sunlight is more intense than the inside light. So that's actually an increase in energy. Okay, if you increase in the energy, the reaction is going to try to shift in the direction, whereas that energy is used up. Okay, So the energy from outside, increases, right? So my reaction should shift to use up that energy. This is an endothermic process. So the reaction should shift to the product side. When that happens, this, the silver ion, like the silver metal, migrates its way to the surface actually, and it makes the glasses darker. Okay, so here we go. Châtelier putting his glasses on here. Okay, and we can see that we're going to shift to the product side, and the glasses darken because that silver makes its way to the surface. Okay, look how dramatic that is. All right, you go back inside, and the energy decreases again, right? There's less sunlight energy, so the reaction is going to shift it back the other direction. The reaction will go back here because we're decreasing our energy, so we want to produce some more, right? So we shift back to where we started, back to the reactant side, and our new equilibrium creates that silver chloride clear component, and the glass is light again. All right, really cool stuff, LeChatelier's principle. So you can take a second and summarize what we did here, and we'll move on to the last one. Okay, quick video clip here on the effect of change in pressure. It's a 2-minute clip, and then we'll talk about it.
The molecule nitrogen dioxide is unusual in possessing an odd number of electrons. The Lewis structure shown here is one of several that can be written for NO2, which exists as a brown gas. Nitrogen dioxide reacts with another NO2 molecule to form colorless dinitrogen tetroxide, in which the odd electrons on two molecules pair up to form a new nitrogen-nitrogen bond. In the gas phase, an equilibrium is established between NO2 and N2O4 molecules. The equilibrium lies heavily toward NO2. When the volume of the system is decreased at constant temperature, the overall pressure increases. Suppose that we were to halve the volume instantaneously. Here is a graph of the pressures of NO2 and N2O4 as a function of time. Notice that when the volume is instantly halved, the pressure of each gas is instantly doubled in accordance with Boyle's law. After this instantaneous decrease in volume, the system is no longer at equilibrium. LeChatelier's principle tells us that the chemical equilibrium will shift in a direction that partially undoes the effects of the volume decrease. That means it will shift in the direction of more N2O4 to undo the doubling of the pressure in the system. The pressure decreases as more N2O4 is formed because the total number of molecules decreases. On our graph of the gas pressures, we see that the decrease in NO2 pressure is twice as large as the increase in N2O4 pressure.
All right, so there are two conditions where changing the pressure does not change KEQ, first of all. So you can write these down. If you add an inert gas, so something like nitrogen or any of our noble gases, it doesn't take place in the reaction. Inert gas means does not react. And the changes, it changes the overall pressure of the system, but it doesn't change the partial pressure of your reactants or products. All right, so the inert gas isn't reacting with anything, so Kp stay the same, Keq stays the same. Additionally, if you have the same number of moles of gas on the reactant product side, equilibrium won't move at all. All right, so moles of gas we'll see is very important when we talk about pressure. So here's your rule, really, really easy. I think this is the easiest one. When increasing the pressure, equilibrium will shift to the side of the reaction with the fewest number of moles of gas. So here is an example of that. So you have two chemical equations here. All right, I'll do the first one with you. You have an increase in pressure. Okay, so pressure is going up. Here's your container with your gas in it. Okay, it has some pressure. If you increase the pressure, there's some piston or something that pushes down, on these gas particles. So the pressure goes up. Well, how can I decrease the pressure then? Okay, so if you have an increase in pressure, equilibrium will shift to decrease it, to undo that stress. So what causes gas pressure? Well, gas particles do, right? So I need to decrease the number of gas particles in my system to decrease my pressure. All right. So for the first reaction, you have 0 moles of gas on the reactant side. You have 2 moles of gas on the product side. So an increase in pressure would change my equilibrium by shifting in a direction so I can decrease my pressure again. So this first reaction, I want to shift it to the reactant side. Okay? So as this reaction proceeds to the reactant side, the gas is coming out of the system. It's turning into a solid. So you have less gas because coming out of the system back into a solid means less pressure. So that's undoing the increase that you put on that system. Does KEQ change? Big time no. All right? Remember, the only time KEQ changes is with a change in temperature. Previous one we did. Okay, second one, you can give it a try. We have 2 moles of gas on the reactant side and 1 mole of gas on the product side. So how did an increase in temperature affect equilibrium for that one? Well, if you take a look at it, we have an increase in pressure. Reaction should shift in the direction to decrease the number of moles of gas. So 2 moles of gas on the reactant side, 1 on the product side. Reaction moves to the right big time. Okay? That's it. That's your change in pressure and how that works. Really easy. You just want to undo the stress placed on the system and just make sure you could explain it properly if asked. Okay, practice problem to wrap it all up here before we do one real life example. Which of the following will result in an equilibrium shift to the right? Okay, so you have your reaction here. You got to figure out, is it an endo or exo reaction? I give you a delta H of negative 87.9. That should tell you if it's endo or exothermic. And then look at how many moles of gas are on each side. Okay? You want to figure out which one of these 5 answers is going to give us what we want. Okay, so take a second, try to figure it out, and we'll go from there. Okay, so what we want to do here is shift the reaction to the product side. Okay, so it's exothermic, first of all, because this is a negative H value. Okay. And we have 2 moles of gas on the reactant side and 1 mole on the product side. Let's start with pressure first. That's easier. If I want to shift the reaction to the right, that means I'm going from 2 moles of gas into 1 mole of gas. So if I shift this to the right, that means the stress I placed on the system was an increase in pressure. Okay? So I increased my pressure on the system because it forced my system to go to the right, which is less moles of gas. So which one of these, it's clearly not 5, which one of these is going to cause an increase in pressure? Well, from the little video clip, a decrease in volume will cause an increase in pressure. So 5 is out. An increase in volume for number 3 would cause a decrease in pressure. Well, that's wrong. Same thing for number 1. Okay, so 1, 3, and 5 are out. So now we're down to temperature. It's an exothermic reaction, so the energy is on your product side. Okay? If I'm shifting to the product side, which is where I'm creating more energy, that means the reaction was probably stressed by me decreasing the temperature. So if I decrease the temperature, the reaction will proceed in a way to increase it again by releasing energy. In this case, moving to the product side because it's exothermic. So that gets rid of number 2. A decrease in temperature will cause me to increase it again. So I'll shift to the product side where the energy term is. And then a decrease in volume. Remember, pressure and volume right here have an inverse relationship. Decrease the volume, increase the pressure. So my reaction will shift to try to get rid of that increase in pressure by creating 1 mole of gas. All right, so there we go. We got it right, number 4. Okay, last part of this. I could kind of skip over this, but I think it's really, really cool. I'll try to go through it quick because this is a longer lesson, and I'm aware of that. But it's the last big lesson for this unit, actually. Making ammonia is a equilibrium system, all right? So you have H2 plus N2 yields 2NH3 gas, all right? Nitrogen and hydrogen are abundant. Can ammonia easily be made? It seems like it would be, but if you look at this, look at the Kc value at 400 Celsius. 1.1 or 1.64 times 10 to the negative fourth power. This is extremely what? Okay, well, that's extremely reactant favored. Okay? Well, to make ammonia, that's a product. I need it to be product favored. So at a really high temperature, this is not that easy to make because look, even at a high temperature, it's reactant favored. So let's take a look at this process real quick. The importance of ammonia is because it's used in fertilizer, so it's really, really important in agriculture. And it's also used in something super important like making things blow up. All right, so explosives. KNO3 is, it can be used to make KNO3, which is an explosive. So the history of ammonia real quick is that most of this is made in just one part of the world, right here, okay? And during World War I, the Allies controlled Chile and cut off supply of the ammonia production, basically, and the KNO3 to Germany. So Germany had to figure out a way to make this itself because it needed to make its own explosives for World War I. So, some German scientists came up with this idea of how do I get my equilibrium system to shift to the product side as much as possible, right? Because we just saw that making ammonia is very reactant favored. So, how do we get it to be more product favored? Let's take a look at it. You can do 3 things, or 4 things, I guess. One of them is to actually take, the hydrogen and nitrogen and add more of them. So if we increase the amount of nitrogen, increase the amount of hydrogen, that is going to take our Q value and increase our reactants big time, right? Because Q is products over reactants. So if I make my nitrogen and hydrogen really, really big, my denominator is becoming huge. So I'm going to make my Q value less than K. I'm going to push this to the right big time to make some more NH3. Okay, so that's pretty obvious. One thing you can do. Add hydrogen or nitrogen. Another thing you can do is when you make the ammonia, take it out of the system. All right, because the ammonia is a product. Right, you had your hydrogen and nitrogen as your reactants. If you take your ammonia out, right, and you decrease the amount of it you have, that's actually going to take your Q value, which is products over reactants. If you take your ammonia out, that's your product. If you take it out, then your Q value becomes less than K again, right? Which makes us shift to the product side. So as you take more ammonia out, you're going to make more ammonia. Take it out, make more. So that's something else you could do. Something else that you could do is look at what happens here. At high pressure, in the 1900s, they figured out how to do this. You can complete this reaction and push it to the product side even more. All right, so if you look at changing the pressure, we focus on moles of gas. So we have here 4 moles of gas, and here we have 2. Okay, so if I increase the pressure by a lot, it's going to cause the reaction to shift in such a way where the pressure will decrease again. So if there's 2 moles of gas on the reactant side, 2 moles on the product side, if I make a really high pressure system, the reaction will shift to the right to decrease that pressure, create more NH3. Last one. This is an exothermic reaction. The delta H is negative 92 approximately kilojoules. So what you can do is run the reaction at a really low temperature. If you run the reaction at a low temperature, it's going to push it to the right, okay? Because it's exothermic, so the energy term is on the product side. So if you decrease the temperature, reaction will shift in a way to increase it, push to the right, okay, create more NH3. The problem with that is at low temperatures, the reactions usually go slower. So you'll make more NH3, but at a slower rate, okay? So it's still not that good. So what they figured out was they can add a catalyst. You know from Chem 1 that a catalyst increases the rate of your chemical reaction. So for equilibrium systems, it increases the rate of both the forward and reverse reaction. So if we can add a catalyst with a low temperature, we could push that reaction to the right, okay? We could push the reaction to the product side, okay? And with a catalyst being used, we could push it to the product side faster, all right? So the low temperature is a hindrance because the reaction goes slower, but as you add the catalyst, it makes it go quicker, and then that low temperature makes it go to the product side more. So it's shifted more to that product, which is NH3. Okay, there's a quick history of that at the end here. Just one example of a real-life application for LeChatelier's principle in equilibrium. I think this stuff's really neat. This is one of my favorite lessons of the unit. It's also one of my favorite labs as well. So we'll get to that pretty soon. There's a little bit of homework on LeChatelier's principle, but if you go back in through this, you should be fine trying to figure out those answers. And if you have any questions or concerns, we can talk about them in class. All right, thanks guys.